Okay, in this example, I want to show you the contribution of radiation in comparison to free convection. Let's draw a roof and this roof has a certain temperature T roof. And this roof is insulated below, and the sun is shining the whole day because it is a really nice country on this roof. And the amount of energy which is coming to the roof is 300 watts per square meter of the roof. The surrounding air, here, T air, is 20 degrees C. And you can imagine that this roof becomes really hot. So this is a hot place and the air becomes very hot, and here above we have cold air. So what we get is, we get a free convection as a result of density difference of the air which is going upwards. So you can imagine that in this way energy is lost while energy is also coming in. Well, how do we calculate the contribution of free convection? Well, we have learned that if we want to calculate how much heat has lost, we say, okay, phi q, the flux is equal to the heat transfer coefficient multiplied by the temperature difference. But in this case, we only know the temperature of the air and not already the temperature of the roof. So the question is, what will be the temperature of the roof? Can we say something about that? Well, how do we calculate the heat transfer coefficient? Then we need a correlation to calculate it. We have learned to look up the correlation which is applicable for free convection of a flat plate. Well, if you look up this equation, you will find that it will be a correlation where you will find a Grashof number and a Prandtl number to the power 1/3. So from this Nusselt number, we can say the heat transfer coefficient is equal to the heat conduction divided by a characteristic length multiplied by the Nusselt number. Well, what's the characteristic length? Well, you could say that is the length of the roof. Well, let's say that this is 10 meters, for example. Then you have the number of things which you have to calculate. Well, what's the Grashof number and what's the Prandtl number in this case? Well, we have seen that the Grashof number is equal in principle to the buoyancy and gravity, but we could write it a little bit differently. We could say that is the characteristic coefficient L3, and I have to look up it carefully, multiplied by the gravity, divided by the kinematic viscosity squared, multiplied by gamma, which is the cubic expansion coefficient, multiplied by delta T. Okay, that's nice to see, but now the question is, how could we derive the cubic expansion coefficient, gamma, in this case? Well, this gamma is equal to 1/v dv dt in case of an ideal gas. This will be, you can find it out if you put in the ideal gas law, you will find that this is equal to 1/T. So in this case, we can calculate the Grashof number. Well, the Prandtl number, we know, is the ratio between the kinematic viscosity and the heat coefficient A. So in this case, we can also calculate the Nusselt number. But still the question stays, what's the temperature of the roof? How can we derive this one? Well, let's compare these equations a little bit. You see that in the Grashof number, there is a delta T. And you see that if we put in, so in the Nusselt number, in fact, there's a delta T. But we knew already, so we knew already how much phi q was. So in fact, we could say H is in principle also the flux divided by delta T. So in fact, we have now two equations with which we can eliminate delta T. If you eliminate delta T, you will find a value of delta T of 43 degrees Celsius. So that means that the roof is 63 degrees C. Subsequently, you can say, what's now the contribution of radiation? Yeah? Now you can compare these two. We knew already that 300 watts was already, let's say, coming in. So we knew that 300 watts was already entering. The question is the 300 watts compared to the radiation contribution, is that low or high? Well, how did we calculate the flux by radiation? Well, the flux by radiation, we used the equation in which we had an emission coefficient and a sigma multiplied by T to the fourth. That was the Stefan-Boltzmann equation we already knew. Well, assume that this is a black body, so E is in this case 1. If we now substitute the value of, in here, substitute the value of the roof of 63 degrees C, we can calculate the value of this heat flux. And if you calculate that, we get a flux of about 300 watts per square meter. So you see that it is really a tremendous amount contributes to the radiation in this case. So if you compare now this value with the one of the 300 we started with, you see that it's nearly doubled. So radiation is really important. Let's sum up the total. We started with a roof where the sun was entering, and we got 300 watts per square meter. We looked, our question was, how could we calculate T-roof? We combined two equations because we knew already the value of the flux, and we knew an expression of the heat transfer coefficient. Both contained the delta T. We eliminated the delta T, and we got a temperature difference of 43 degrees C. Subsequently, we calculated with the obtained value of the roof, which was here, we got T-roof. In fact, is 63 degrees C. And we calculated the contribution of radiation. And now we can compare the total heat loss of free convection and radiation. Thanks for looking.